Okay, so in starting, I'm on Kim Libre uh, that I create those links for you. It's a free online textbook in case you don't know. And then if you scroll all the way to the bottom, then the summary and key takeaway, I think, are the most important aspect. And so uh, in intermolecular forces, then first you just have to learn the different names and when to recognize them. If you read this, then that's the best part. All right, start with the summary, the abstracts, those kinds of key concentrated things. And if you'll scroll up, you'll see that just like the normal kind of pattern, it's a good story if you want to read it, but most of the time you're here because you don't get it in this linear type fashion. All right. So I'm going to switch over then. Wikipedia is another good source to find stuff. And again, this is the key takeaway from it. And you have to scroll down to get to this important thing. So if we look at the bond types, then we have London forces here. They're present in all molecules, but they're very weak. All right. And they can be strong because it's like Velcro. All right. If you have a small piece of Velcro, then the forces are small. If you have a big molecule and you get a bigger and bigger piece of Velcro, then they can become strong. But let's put that in context with at the other end of the extreme, we have this ionic lattice. All right. And so here, if you'll notice, they're presenting both kcal and kilojoule. In my class, you don't need to know this number. We just need to be able to recognize them and label. But this magnitude, I think, is a very clarifying point. All right. In the book that we're using, ionic bonding is not considered an intermolecular force, and it's not really relevant to the molecules and stuff that we're looking at. So it's more associated with lattice energy from the first semester. All right. But this is pure ionic bonding, is all it is. And we can see the order of this number. It's incredible. And so covalent bonding, bond enthalpy, you learned last semester again. That's in, intramolecular. All right. So the bond overlap covalent bonding, and that's very different, right? And so now hydrogen bonding, dipole, and London forces are those kind of key things that we're wanting to recognize. So everything has London force, dipole, and hydrogen bonding, and ion dipole that's not shown here is what you want to be able to get. All right. So now if we'll scroll back and we go back to the Kim Libre, we can see dipole. So what is dipole? Dipole interactions are where you have unequal bond uh, sharing. So pure covalent bonding is they're sharing electrons in order to reach the octet rule, and this is classically non-metal. And so if we have metal, non-metal, that's where we get the ionic that we were talking about before. So as we start to deviate though, and we get that difference in electronegativity bonding two different elements, that's where we get this unequal distribution. And when we have that partial charge, then they'll interact with each other, and this creates that additional interaction. All right. And so that's what's called dipole. And so you can have dipole induced dipole, pure dipole. Those are uh, don't focus on that fine detail. Focus on the big picture, and then you can come back. Now, as you scroll through, you can see this Kim Libre has examples and doesn't have a ton of examples. That's why I recommend your book. But if you're not getting it from your book, going to YouTube or other sources, then they're good. All right. So now London force, we talked about all molecules have it. And so we can see we often use it to describe simple ones because they don't have anything else, right? You don't have two different bond interactions, so you can't have a dipole moment. And so here you could have a dipole. And remember, for that, what you need to look at is Vesper. Do you have one lone pair? Then you're going to have a dipole. And or do you have unequal break that symmetry by not having all CH4. If you had CH3Cl, now you break that symmetry from the dipole on. So, scrolling down one more, hydrogen bonding, and these are pretty simple to recognize. So here's this classic trend showing you that it's different. So what happens is that when you have hydrogen bound to one of these really electronegative elements, you're pulling that electron density towards that electronegative, and you're leaving behind the proton. There's no core electrons. So this is on order of those ions that we were talking about. So we start to get to ion dipole interaction. And we can see if we look at the trend here that it really breaks that trend because that's a stronger interaction. Okay, so scroll through it, look at the end. There's some example problems here you can think about and some answers for you. But let me know if you want more detail or not.